sklearn, linear model, SGD1ClassSVM. Description. This class implements a one-class SVM using a stochastic gradient descent (SGD) method. It can be used to detect novelties or outliers in data. The model learns a boundary that encapsulates the normal data points, and any data point outside this boundary is considered an outlier. Inputs: X, a NumPy array of shape n samples. N features representing the training data. Y not applicable as this is an unsupervised learning method. Outputs: self the fitted SGD1ClassSVM object. Decision function X, a NumPy array of shape n samples, containing the decision function values for the given data points. The decision function gives a score for each data point, where a positive score indicates that the point is likely to be an outlier. Steps. Initialization: initialize the model with the specified parameters. Training: use SGD to train the model on the given training data. The model learns the hyperplane that separates the normal data from the outliers. Prediction: use the fitted model to predict the decision function values for new data points. Metrics. Accuracy: the percentage of correctly classified data points normal vs. outlier. Precision: the ratio of correctly classified outliers to the total number of predicted outliers. Recall: the ratio of correctly classified outliers to the total number of actual outliers. F1 score: the harmonic mean of precision and recall. Visualization plots. Scatter plot: plot the data points in a 2D space, color coding them based on their decision function values. This can be useful for visualizing the learned decision boundary and identifying outliers. Fine-tune parameters. Penalty: the type of penalty to use for the loss function. Possible values are L2 L2 penalty and L1 L1 penalty. Alpha: the regularization parameter. Fit intercept: whether to fit an intercept term. Maxiter: the maximum number of iterations to run the SGD algorithm. Toll: the tolerance for the stopping criterion. Shuffle: whether to shuffle the training data before each epoch. Random state: the seed for the random number generator. Uncertainty methods. Confidence interval: calculate confidence intervals for the decision function values. This can be used to quantify the uncertainty in the model's predictions. Challenges and fixes. Challenge 1: overfitting to the training data. Sample use case that resulted in challenge 1: a dataset with a small number of outliers may lead to the model fitting the outliers too closely, resulting in poor performance on unseen data. Fixes to challenge 1. Increase the regularization parameter alpha. Use a smaller value for the penalty parameter. Reduce the number of iterations. Challenge 2: difficulty in handling high-dimensional data. Sample use case that resulted in challenge 2 in datasets with a large number of features. The model may struggle to learn a meaningful decision boundary. Fixes to challenge 2. Feature selection: select only the most relevant features for the task. Dimensionality reduction techniques: apply techniques like PCA or T-SNE to reduce the dimensionality of the data. Challenge 3: sensitivity to the choice of parameters. Sample use case that resulted in challenge 3: the performance of the model can be highly sensitive to the choice of parameters, such as penalty, alpha, and maxiter. Fixes to challenge 3. Use grid search or other hyperparameter optimization techniques to find the best set of parameters for the given data. Perform cross-validation to evaluate the model's performance on unseen data and ensure robustness.